Okay, so chemical reactions have a certain activation energy, and it would be nice to know what that is. And that's where the arrhenius equation comes into play. The idea is that since activation energy depends on the reaction rate and the temperature, and some sort of frequency factor that's unique for each chemical reaction, there must be a way to calculate it. Here's the calculation that the equation as it came out. Before we go into too much detail, be aware that we'll be talking about specifically how much of this you need to know for AP chemistry. But let's go ahead and take a look at it just in general. The idea is that the rate constant will be equal to some frequency factor unique for that chemical reaction times e to a certain power, and that power is negative E sub A. There's the activation energy right there. So in principle, we should be able to rearrange this to solve for the activation energy, something that would be nice to know. Divided by RT, something you see in a lot of equations, that's a constant, and T is the Kelvin temperature. So there is a temperature dependence on the activation energy, the rate constant comes into play, and the frequency factor comes into play. So as you might imagine, let's take a look right here. Calculations involving the arrhenius equation are beyond the scope of this course. It can get very tedious and you get lost in the math. You need to know that that this exists, that what factors come into play, and we just outlined them. And you should also know that if you do plot the natural log of the rate constant, which by the way, rate constant is 1 over time, against the inverse of the Kelvin temperature, you get a slope, a line with a straight line typically with a slope, and that slope is the activation energy. Technically it's the activation energy divided by a constant, but that's just a number. So you will typically get numbers between 1 and 100 kilojoules per mole, and that is the activation energy for that chemical reaction. Okay, that's the stuff you need to know. What's involved in the equation, how it can be graphically interpreted to get the activation energy directly, and really what you need to know. I want to read these both in their entirety. The College Board states, the arrhenius equation can be used to summarize experiments on the temperature dependence of the rate of an elementary reaction. That's basically what they want to focus on. And to interpret this dependence in terms of the activation energy needed to reach that transition state. So really they're saying there's a temperature dependence there. They're not focusing as much on the frequency factor or the rate constant, mostly that there's a temperature dependence. And then they say, hey, you don't have to do any calculations for it. That's right there, and that's wonderful. And the rationale, let's go ahead and read it. The conceptual aspects of the arrhenius equation and the interpretation of the graphs, bing, 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 that's part of the course. However, the inclusion of the algorithmic calculations was not viewed as the best way to deepen understanding of the big ideas. I think that's code for saying, oh, it's tedious and you don't learn much from it. Adrian Dingle interpreted this recently as saying this is a bit of a red herring since calculations have hardly ever been asked in a contemporary exam. Really, the only useful application is in a y equals mx plus b plot. I suppose that's this. To determine the activation energy, and that's what you really are using to determine the activation energy. So not a calculation as such, it's a use of a graph. I will continue to include it in that context and continue to exclude complicated arrhenius calculations from my course. I'll be looking for specific post-2014 AP released items that might include the arrhenius equation to see if there's any at all out there. Okay, that's a little bit about the arrhenius equation as it applies to AP chemistry.